Okay, sir. So you're all welcome to this month's presentation. We are lucky to have the past president of our society, a father to me and many others that will be listening today, a teacher, a mentor, in no other person than Professor Sam Adefila. I think out of all the days I've been hosting this presentation, today is a special day for me. For me to be hosting this presentation while my father, teacher, mentor will give the talk. Initially, I wanted to sway away from giving the presentation. I wanted somebody else to handle it, but he insisted that I should do it. Thank you very much, sir, for honoring us to give us talk this month. Our program of events, we are going to have the program starts 5:30, safety moments, brief profile of the guest speaker presentation, questions and answers, recap, then a vote of thanks by my NSChE HAC lead, Engineer Abubakar. So I wish to welcome all our senior colleagues, fellows, members of the society. I'm just tracking, I don't know if I have the president around, but everybody around, you're all welcome to this month's presentation. Our safety moments for this week, I'm going to share a video. I'm going to play a video. That video is going to be our safety moment. So in a minute, I'll share the video. Here we go.
Officially, yeah. Goodness me. How did you know what to do? Well, I have had some training in the past. As you can see from the video, really, I didn't expect it. I thought it was fucking around, to be honest. So we probably built our training sessions. That's what was going on. The iPhone was recording your sparring session, wasn't it? Exactly. If you've never had the training, should you still do it on someone? Yeah, absolutely. The very worst thing you can do is nothing. Right, okay. Anything is better than nothing. Mark said he was dead. So you're not going to make that situation any worse at all. And actually, when you dial 999 these days, the operator at the other end, the emergency service operator, will help you and coach you through it. You shake them to see if they respond. Can you hear me? Can you hear me? There's no response. Shout for help. Help. Get somebody to dial 999 or do it yourself and start doing CPR, which are 30 chest compressions. Press hard and fast in the center of the chest with your weight right over. If you're able to do the rescue breaths, tilt the neck back, hold onto the nose, cover the whole of their mouth with yours. 2 breaths, and then back to 30 compressions. Keep doing that. It is hard work. You need to move the chest about 4 to 6 centimeters in to try and make it as effective as possible. But do something. The worst thing you can do is nothing.
Yeah, it's a short video. I think I'll replay it again once more.
Officially, yeah.
How did you know what to do?
Well, I have had some training in the past. But as you can see from the video, really, I didn't expect to to be honest. So we normally film our training sessions.
That's what was going. The iPhone was recording your
Yeah.
sparring session, wasn't
Exactly.
it? If you've never had the training, should you still do it on someone?
Yeah, absolutely. The very worst thing you can do is nothing.
Right. Okay.
Anything is better than nothing. As Mark said, he was dead. So you're not going to make that situation any worse at all. And actually, when you dial 999 these days, the operator at the other end, the emergency service operator, will help you and coach you through it. You shake them to see if they respond. Can you hear me? Can you hear me? There's no response. Shout for help. Help. Get somebody to dial 999 or do it yourself and start doing CPR, which are 30 chest compressions. Hands pressed hard and fast in the center of the chest with your weight right over. If you're able to do the rescue breaths, tilt the neck back, hold onto the nose, cover the whole of their mouth with yours. 2 breaths, and then back to 30 compressions. Keep doing that. It is hard work. You need to move the chest about 4 to 6 centimeters in to try and make it as effective as possible. But do something. The worst thing you can do is nothing.
Thank you very much. The video is self-explanatory. Why it's important all of us learn CPR. It might be the only thing that saves somebody's life, as we've just seen in this video. That's our safety moment for this month. I'll quickly go through the abridged version of Prof. I'll go through the abridged version of Prof's profile. Professor Engineer Samson Adefila was born on 15th August 1949 in Ilofa, Kwara State, Nigeria. He had merry-go-around primary school education, starting from St. Peter's, Ilofa, 1954, through to St. Paul, Ishapa, 1955, St. Peter's, Ilofa, 1956, Baptist Kanu, 1957, United Ilori, 1958, St. John's Bidda Holy Trinity Kanu, 1959, St. John's Katsina, 1960, and finishing in St. Peter's, Ilofa, 1961-62. Wow. So we need to, how many primary school Prof attended? 1, 2, 3, 4, 5, 6, 7, 8. 8 primary school in 6 years. Wow. He received his secondary and higher school education at the government secondary school Ilori from 1963 to 1969. After bagging a BSc degree in chemistry in 1973 from Ahmadu Bello University, he served in 1973-1974, the Guinea Pig National Youth Service Corps. That means they were the founding corps member for the NYC. He joined Ahmadu Bello University in 1974 as an assistant lecturer and rose to the rank of professor in 1990. Meanwhile, while he utilized collaboration program between ABU and the Twente University, the Netherlands, to earn MSc in ABU, PhD in England, PhD in England in chemical engineering in 1977 and 1983, respectively. Outside hundreds of undergraduates have passed through him, he has directly, successfully supervised over 40 postgraduate students. You can count me among the undergraduates and the postgraduate students he has supervised. Many of these graduates have reached the zenith of their career in public and private sectors, including professorial cadres in the universities, group managing directorate levels in group of companies. Besides, he has published over 100 academic papers and consulted for more than 30 industries on energy, environment, feasibility study on process industry, many of which have already been established, and management. He has also served as head of departments and dean of faculty in ABU Zaria and Covenant University. He has served as accreditor of examination in many universities and on behalf of National Universities Commission. He has also served as the chair of many high-powered committees in the university, professional bodies like the Nigerian Society of Chemical Engineers, Nigerian Society of Engineers, Church and Community Development Association. He is currently the deputy national, He is a past president of Nigerian Society of Chemical Engineers and Baba Ijo of the Cathedral Church of St. Peter, Ilofa. One of his most thrilling services is that he was the inaugural chair professor of Petroleum Technology Development Fund, PTDF ABU, which offered his team the opportunity to develop the fundamentals of producing zeolites for petroleum refining from local kaolin and low-grade chemicals. He has advanced this since leaving the chair. For example, a product of these advances is presently undergoing tests for industrial application. Apart from considering the extension of the formation of zeolite beyond linking the columns, 3 and 4 elements to other contiguous elements to produce novel advanced materials for industrial and domestic applications. Professor Adefila voluntarily retired from full university services in February 2014 to serve as chairman of Engineering and Environmental Management Services Limited, EEMS, Abuja. He is also developing a medium-scale agriculture and mineral processing enterprise, ILF Infinite Affair Limited, in his local government area for the purpose of empowerment and inspiration. Together with his deceased wife, Professor Adefila has 4 children, all of who have graduated, contributing to human development in public and private establishments. On behalf of Nigerian Society of Chemical Engineers, I welcome our father, our mentor, our teacher to this month as our guest presenter for this month. Sir, you are highly welcome. Please go ahead and share your slide and take over the proceedings, sir.
Sorry. I'm sorry. Okay. Good evening, everybody. I'm sorry. Okay. Subject of today is Earth's energy budget, available options for human intervention. If you want to understand this thing better, just imagine yourself to be inside a building with all its superstructures and the sun around you, with possibilities of having ACs inside, you have a fan inside, and you can close or open the windows to control the environment within. So that's what we are likely to do today. This is the outline, the Earth's solar system within the Milky Way galaxy, the Earth and its environment, global energy budgets arising from solar-Earth interactions, solar Earth thermal energy budget valve, that is the hydrologic thermodynamic heat engine, which we'll be concentrating on today. Then we have some thermodynamic data on the Earth's atmospheric components, features of climate change, available human interventions and resolutions of climate change, unidisciplinary approach and their wicked problems, multidisciplinary approach with their more friendly, results using pestle framework, then conclusions. This is our Milky Way. Mind you, our Milky Way is just one out of very many galaxies in the universe. Our neighboring galaxy, our Milky Way alone, has an estimated diameter of about 100,000, to 200,000 light years, and a thickness of about 100,000 light years. It has about 400 billion stars, and each of those stars has its what do you call it? Well, I'm sorry, I just something just went off me now. So anyway, so our neighboring galaxy is about twice our own. Therefore, you can imagine how seemingly insignificant we are, within this, system. The Earth is just but one out of so many. Sorry, our Sun is one out of so many stars that you see in the heavens here. And you could see where I showed, I'm sorry, where you could see us, where I showed our own planet within this galaxy. Our planet, our stars within, which is our Sun, within this, among these over 400 billion stars. And here we are. So we really look insignificant, but extremely precious. When you talk about the Earth, you are talking about the geosphere, which is a solid part, which consists about 29% of the surface area which you see today. Then the hydrosphere, that is the waters in the oceans, in the rivers, and so on and so forth, which consists about 71%. Then you have envelope of atmosphere around us, which are in layers, about 5 layers. We are going to see them. And you're going to see how man has been able to understand and be able to manage these various envelopes. I've shown here, a few things on Earth, but the thing which I wanted to take note, like I just said, at our land surface, that the geosphere consists about 29%, and the remaining surface is water. I'm sure you'll not be surprised. You'll see why later. Later on, I'm going to make presentations of the various parts of our atmosphere. So we can divide it 3 parts here, but what's important for us, the most important thing for us is this one that shows the temperature profile, and this one that shows the profile of, pressure. So this one, let me just jump over it because we are going to see, but look at it here. You have troposphere up to about 20 kilometers, the stratosphere starting from there, and so on and so forth. But I'm going to concentrate more on the troposphere and the geosphere because the troposphere constitutes about 80% of the total mass of the atmosphere. And it contains about 99% of the water vapor, and aerosols. And you will see why I'm talking about this, later. So here we have the profile, temperature profile. You could see on Earth, we have the temperature about average of about, say, 20 degrees or something of that nature, and it reduces into the troposphere. You could see it reduces to about -60. And you see that your aeroplane flies through this area of the tropos. And that's why sometimes when you're in the aeroplane, sometimes, most of the time, you see the clouds below you. But sometimes you see some above you. And you know what happens to you when you pass through a cloud. We'll see why it happens. And you see the ozone at the lower part of that stratosphere there. What you see a temperature inversion around that ozone. That ozone prevents some type of radiation from coming in. And you could see, that's why you have accumulation of heat above the ozone. So if this radiation is supposed to be able to pass through the ozone, we will have more heat on Earth. So the ozone is very, very important to us. So take note of that. I think that's what you should take note of here. And in the next slide, which shows the pressure profile, you will see why aeroplanes fly at about that 12 kilometers or so, because the pressure is very low and friction is very, very low, or even nothing. If they are going to fly lower than this, then they'll be going against, a lot of friction. Here I have the composition, components and composition of some materials in the air. We have nitrogen, which consists about 78%, oxygen, which consists about 21%, argon, about 0.9%. So all these you see together consist about 99.9%. But they are not too significant in terms with respect to climate change, which I'm going to be talking about. The most significant ones are these carbon dioxide, methane, and so on. So which consists of just about 0.1%, but are very, very critical. I've already talked about the ozone, earlier on. So how then here we can have water vapor consisting about 4% of wet air, but usually it's an average of about 2%. But that is very, very significant. What's the significance of this? Well, it seems as if the most important thing we see every day is night and day. But there are more important things happening. When solar energy, that's able to penetrate the ozone and reaches the Earth, when it comes, it evaporates water, changes water to water vapor. And you will see why it rises later on, because of the importance of some particular parameters of water. In this particular case, we know that when water vaporizes at a temperature of about, when it changes from liquid to vapor at a temperature of about 100 degrees C, you have about 20,000 times, increase in volume, and so on and so forth. Therefore, the density decreases dramatically and is able to rise. This one, the rise of the air, of water vapor, constitutes the wind system of the world, which is very important for so many things. That's why we're able to breathe fresh air, pollination is taking place, so many other things happening there. And we'll see that this phenomenon that I've just described is actually a thermodynamic heat engine. It's a heat engine. It's not physical. It operates thermodynamically. So from here, we see the amount of radiation which is coming to Earth, passing through about 342. But of this, quite a bit, is reflected back. And we have about 168 watts per square meter, accumulated, on Earth. This is the one which we say causes evaporation of water on about 72% of the surface of the Earth, and over some other parts, the bushes, and and so on and so forth, the biosphere. So essentially, this is what we are talking about. The left-hand side of this picture shows the radiation coming in, and the right-hand side shows what's going out. If you leave this alone, just to happen like that, without that thermodynamic heat engine which I talked about, we'll have a deficit of, we'll have accumulation of about 168, watts per square meter, within the, troposphere, which is going to raise the temperature. And when the temperature rises, we'll see the effect later on. I've talked about this already, that the atmosphere consists, all those nitrogen, argon, oxygen, and coal. It's about 99.9%, but they don't matter too much with respect to thermal control on Earth. But that water, which is just about 2%, becomes very, very significant. This is a table which will be a good take-home for you. For those, whether you like thermodynamics or not, the fact is that there are three important parameters here. The specific heat, CP. I'm sure we know what CP is. CP is the amount of heat that is either transferred into or leaves a material per unit mass to raise the temperature by 1 degree C. And you see for water is 4.18, and I have some others there. For those of us who are curious, you may see that of carbon dioxide, 39%. What is the importance of this? It means when heat, comes into water, you need about 4.18 of, a kilojoule per kilogram before you can raise the temperature by 1 degree. And see some other like, say, methane, which is about 2 point something, and nitrogen is about 1 point something. So you could imagine if that amount of water was not available and covering that large area, about 72% of the surface of the Earth, you can imagine what the temperature of the Earth would have been. But you can also imagine that if this water had been replaced by carbon dioxide, you can also imagine that the temperature of the Earth will fall dramatically. But some other things. The heat engine, which I'm going to show you later on, the latent heat of vaporization is very important. See that of carbon dioxide here, 60.1 kilojoule per kilogram. Then look at water, 2,429. So it means in a cycle, that amount of heat is removed, from the Earth. If you replace water with carbon dioxide, that will not happen. So then this VVVL, that is the ratio of the specific volume in the vapor state to liquid state at equilibrium. So that means at 30 degrees C, for example, when you change liquid water to vapor, the change in volume is about 32,000 times. And if you do that about 5 degrees C, the change in volume is about 200,000 times. So we're not going to touch while terrible winds occur in some places and so on and so forth. You could see the amount of wind that this will cause. Now, let us now come to that thermodynamic heat engine. This is a typical heat engine here. Your heat engine causes liquid to evaporate at a high pressure, high temperature, assuming, say, for example, at 30 degrees C, and it changes to vapor. When it changes to vapor, if you expand it, wind effects take place. So you could see this wind effects. So you could see how that this thermodynamic heat, our thermodynamic heat engine, causes wind effects, and you know the importance of wind to us. Then it now condenses at a temperature of about 5 degrees C. If it condenses at a temperature of about 5 degrees C, mind you, in the air, you saw the other time that the temperature could be about -60 in the tropos. So you could see that the VVVL at that point will be about, say, 1 million times. So you could imagine the kind of wind system that you have, in that place if there was water there. Then it changes to liquid. In a heat pump, you have to pump it. In a heat engine, sorry, you have to pump it. But since our reduced pressure is in the air and our high pressure is here and high temperature is here, so I've now inverted the heat engine. No, I inverted the pH diagram so that you can see as we go up, pressure reduces and temperature reduces also. So you can see it better this way. I hope you can see. So I think I've already explained that. From here, you change liquid. You could see that you have pure liquid here, and you change it to vapor. At from 1 to 4, something like that. Then the vapor expands here, condensation takes place, and rain. So in this particular case, the rain will fall on its own. The wind will go on its own. We'll see the effect of all this later. Imagine if the space we have in the air and atmosphere were not as big, wind effects would have been stronger than it is. This goes in 3 dimensions. It can go laterally, horizontally, can go up and go to Z also. And the rain falls, right here. We're not going to we're going to see some things later. I can just explain it here. The capacity of this heat engine is dependent on the temperature of this evaporator, the temperature on Earth, and the difference in temperature between this and where the condensation takes place. So if there is anything that will increase the temperature here, it means the capacity of this heat engine will change. And I can also say here, if you're not careful, you think that we have one big heat engine on all over the Earth. But you could see the geography of the Earth is such that the Earth rotates, spins. And when that happens, the amount of sunlight on a particular place to another place differs. So you have this heat engine, dispersed in terms of time and space. So when it's raining around us, say in West Africa here, it is not raining elsewhere. Then I can also try to explain the effect of this wind to us. All of us did some geography. On wind, if you have a large landmass, like say Africa, America, and so on and so forth. Imagine Africa, for example. If you have vapor passing over large expanse of ocean, it carries a lot of water. When it carries that water, it comes over land, and the pressure starts reducing. When the pressure starts reducing, it means it's the ability to shed some of to convert some of the water vapor to liquid, also will start increasing. And you could see that's why sometimes it may not be raining along the coast, and it will be raining right inside there. So we'll have a lot of rain along that windward side. and it continues to shed its water vapor as it goes over the large expanse of land. By the time it penetrates inside, it has dropped this wind, current vapor, has dropped all its vapor, and it continues to blow over the biosphere. If it continues to blow over the biosphere, it will now start picking, because of equilibrium situation, it will now start picking water inside over land. And that's why sometimes you have forests on the windward side and you have desert over the other side. And this is very important for us when we start, explaining climate change. I've told us that when climate changes, that is as a result of two things. One, if you destroy ozone layer, more ultraviolet radiation will come in and increase temperature on Earth. If you accumulate greenhouse gases within the troposphere, it will prevent infrared ray from going out, and heat accumulates. So it accumulates. It comes as a result of two things: destruction of the ozone layer, then accumulation of greenhouse gases. If you do this, the temperature of your evaporator will increase. And the difference between the temperature of the evaporator and the condenser will increase. And these are the things that lead to the capacity of that heat engine. So as you have more accumulation, higher temperature on Earth, more rains will occur. And on windward side, and more dry wind will be going on interland. So you could see, that's why we have those kind of devastations, say in the US, for example, where New York is flooding, and California, we have dry forests and fire taking place. So I've used this diagram to explain to us what is happening. All these are part of the things which I have been saying, which I've talked about, okay? I put them here for the sake of those who want to go back home and read through to really understand what I am saying. Okay, I've already talked about this. What are the factors that lead to climate change? Net accumulation of solar heat as a result of destruction of ozone layer, allowing ultraviolet heat, ultraviolet radiation to come in more than it should. Then accumulation of greenhouse gases within, which prevent infrared ray, which would have gone out on its own from going out. But thank God the thermodynamic heat engine is there. That is the hydrologic cycle, which picks a lot of heat from Earth to evaporate water and goes into the air, condenses in the air, falls as rain, and the high CP of water comes back to Earth to mop up more heat on Earth, and so on and so forth. So the valve for this heat system is that thermodynamic heat engine, the hydrological cycle. So that's it. We should be careful with that ozone layer. We should be careful with accumulation of greenhouse gases, and so on and so forth. So these are the things. I've already given explanations of these. Rains on the windward side of large land masses and drought inside there. So, therefore, what do we do? The most tempting thing is just straight away apply engineering solution. If you want to apply engineering solution, what are we going to do? We create more channels to allow these floods to allow this water to pass so there will be no flooding. We make the channels wider, we make them deeper, but the water will still go somewhere. Then we can go and accumulate the waters in some reservoirs down there. It means we have to dig big reservoirs. If we dig these big reservoirs, we have accumulation of water here. But since there is drought somewhere else, if we have our engineering strong, we say that, okay, let us pipe this water accumulated here into the dry land. If we do that, what are we going to have? We do that, we are going to have, we have what we call wicked problems or hypercomplex problems. We do not know what effects those big reservoirs that we're going to make, we do not know what they will cause. Then, if we pipe too much water to dry areas, we do not know the effect it will cause. If we do that, it means when dry wind comes to that area, it will have water to pick up. And the climate in the neighboring area will also change. And when you have so many things happening like that, we call this wicked problems, which you cannot resolve. So it is very dangerous for us to say that we apply straight away engineering solutions alone. Because if we apply engineering solutions like it's being done in some parts in China right now, they're changing the soils in their desert. We can also do it. We can change our silica to zeolite. It's straightforward. I'm not saying it's that simple. But if you apply, there is no engineering solution that cannot be applied. When we apply engineering solution, we can get anything we want. We can get anything we want. But we can also have any kind of problems which we do not expect. And this is what we are saying. Therefore, instead of applying unidisciplinary approaches, like mostly engineering will suggest, because we are strong in engineering, and so on and so forth, and leaving other disciplines, we are going to have problems. Therefore, we must apply multi-dimensional or multidisciplinary approaches. And even not just multidisciplinary, but transdisciplinary. If you have transdisciplinary approach rather than multidisciplinary approach, it means you are going to get better results than what we expect. So we expect, we're going to apply what we call the PESTEL framework. PESTEL, that is political, economic, social, technological, legal, and environmental, factors. We bring all these people together rather than trying to, we see what application of unidisciplinary approach in Niger Delta has caused us. So we must now bring in PESTEL to play. And apart from this, human beings have to realize that we are not the only citizens on Earth. Other citizens also are there. We have trees, we have animals, we have earthworms, we have insects, and so on and so forth. Right now, we seem not to care about them. We just go somewhere, dig all that land, dig up everything, chase away all the snakes, chase away everybody, as if we are the only, a citizen on Earth. We are not the only citizen on Earth. Okay. So what do we do? From engineering point of view, reduce ozone depleting materials. If we do that, it means we are stopping some industries from working. You are stopping some people from getting jobs. You are stopping some people from making money, and so on and so forth. But somehow we should control them using PESTEL framework. PESTEL as framework of operation. We must demonstrate better, greater responsibility. And we must realize that we are shared, we must recognize that we must have the recognition of shared global citizenship. We are not the only citizen on Earth. Other citizens also exist on Earth. So, our conclusions. Our solar system is both insignificant within the Milky Way and in fact, within the universe. But we are extremely precious. The Earth's exposed geosphere, geospheric surface area is 29%. That of the hydrosphere is 71%. And we have seen that with a CP of water, that allows us to have a lot of a surface area to absorb heat. And because the CP is high, it can absorb so much heat without translating to temperature rise. So we are lucky with that. And beyond that, we have our thermodynamic heat engine operating there, which helps us. But if we push this thermodynamic heat engine beyond the temperature ranges, which we have now, then we can start having some challenges. The solar-earth interaction without the hydrology cycle presents a thermal engine budget accumulation. I had said that because earlier, that we have extra 168 watts per square meter, which we cannot, which we'll not be able to use. I already told us that we have three peculiar properties of water. That is the CP, the latent heat of vaporization or condensation, whichever way you want to look at it. Then the VVVL. That VVVL is very important. And we easily see the importance of this VVVL when we are flying in an aeroplane. If you are flying an aeroplane and you see cloud, you know that you must get ready for turbulence, because the engine of the aeroplane will evaporate water suddenly. And you could see the VVVL for water in that place, where the temperature is about -50, -60 degrees centigrade. The change in volume from water to vapor around that place will be about, say, 500,000 times. And that's why your airplane will shake when you pass through all these kind of places. That's just talking about simply your aeroplane without talking about other things. I've said that climate change is as a result of uncontrolled penetration of ultraviolet rays through ozone layer. If ozone layer was thick enough, you see that temperature will just accumulate up there and will not come here. If we do not overaccumulate greenhouse gases, the temperature here will also not be as bad as it is. So we know that pre-industrial human civilization impact on climate was sustainable, was managed sustainably by operation of nature's hydroelectric thermal heat engine alone as a valve. And even through our analog industrial era, it was still managed. But the digital age era has actually exacerbated these challenges, and we can no longer contain them. Together with our mismanagement of exploitation of earth resources, one, and we think that we are the only citizen on earth, which is not correct. So, current understanding of technology with application of unidisciplinary approach for abatement of climate change and management of its consequences within the space of within our space, within the troposphere, and mass irresponsible exploitation and poor distribution of planet resources have resulted in wicked or hyper complex problems. Multidisciplinary approaches using PESTEL as a framework will help with man's responsibility, more responsible behavior and the exploitation of planetary resources. Greater recognition of shared global citizenship should be adopted. Then, with what you have said, you imagine that, oh, once we start applying Pestel principle, all will be well. That may not be true. Expecting paradise on earth? Well, I don't know. The great man, Ursula, Franklin, said that not all problems can be solved, but all problems can be illuminated. Thank you very much.
Thank you very much, sir. Thank you very much, sir. As usual, we've had a presentation that's highly philosophical and using engineering to explain some of the phenomena we have around us and how we can address the challenges the world currently faces. Thank you very much, sir, for the presentation. We are very, very grateful for continuously sharing your knowledge with us. And when I had a pre-recording with you yesterday, I was just wondering why you retired from the university. I think we should still be tapping from your wide knowledge, sir, and because you appeared not tired, sir. Thank you very much, sir. So I'll quickly go to the questions I have on the chat for you, sir. I'll read them out. Then for those that want to speak, you just raise your hand in the chat using the icon for raising hand.
Give me 1 minute. Please give me 1 minute to take pen and paper.
Okay, sir. Go ahead, sir. Earlier on, I saw our president, Engineer Saeed Mohammed, but it's like he stepped out. He was around throughout, but I think I think he has stepped out. Our president, Engineer Saeed Mohammed, was actually here earlier on. So thank you, sir, for attending our presentation today. We have our past presidents like Engineer John Erinier, a fellow of the society, and other senior colleagues who have taken their time out to be at today's presentation. In fact, today's presentation, at a certain point, we have about 65 people attending, which is the highest we've had for the past few months. We highly appreciate your time you've taken out to attend Prof's presentation. So Prof, are you back?
I'm back.
Okay.
I'm ready.
Yes, I'll read it out, sir.
Okay.
The first question is that somebody is asking, which I'm sure you will permit, or say, thank you, Prof, sir. May you permit the organizer to send the slides across to us?
Yes. Yes, please.
Yes, we by God's grace, we are going to share the slides with.
I will send a current one to you.
It's okay, we are going to share the slides with everybody. Then the next question is that somebody asks, sir, can you please, what is the meaning of pestle? I'm sure he wants to have more understanding of what pestle is. Political, economic, social, technology, legal, and environmental approach in resolving challenges. Then sorry, I've not been calling the names. I made a mistake. Engineer Tukur Lawal, a senior colleague. So many thanks, Prof, for taking these sessions to another level. The new concept of multidimensional transnational approach is the real solution to climate crisis. You remain the grandfather of chemical engineering in the North and the whole of Nigeria. Congratulations, sir, and remain blessed. Yes, grandfather of chemical engineering in Nigeria. Thank you very much, sir. So that's from Engineer Tukur. Then from Engineer Ion Solar, an excellent presentation, sir. Thank you, sir. From Engineer Bashir, many thanks for this wonderful presentation, sir. Then, and then again from Engineer Tukur Lawal, he says, I remain convinced that synergies between academia and industry, it's is a solution to our challenges we have, definitely. Engineer Yunus AG, appreciations to Prof for the educative presentation. Engineer Ayon Sola, please, I would like to have a copy of this presentation. We'll send that to you. Engineer Mojirade Olurontoba, congratulations to the HSE sectoral group of the Nigerian Society of Chemical Engineers. Congratulations to the HSE sectoral group of Nigerian Society of Chemical Engineers on this 20th monthly technical meeting with the topic as by Professor S.S. Adefila. Good afternoon, distinguished members. Yes, thank you very much. This is the 21st presentation we've been having. Thank you very much. Engineer, okay. Of course, Engineer Tukur is back, harping on why the academia, industry, and the government should work together for the benefit of the society. So what do we do next as a group? Thank you, Engineer James Nano. Thank you so much for your generosity, Prof. Engineer Timothy Sherif. Prof, thanks for the wonderful presentation. So maybe I'll just hold on. You still have a lot more to come. Maybe I'll allow you to address one or two. Most of them are comments. Most of them are appreciation.
Yeah. The only thing I have to address is PESTO.
Yes, sir.
PESTO.
Yes, sir. Go ahead, sir.
PESTO, as a framework, you know, those of us in academics, when you explain, when you talk about PVT, and you've not used the graphical approach, you don't see it sufficiently. But when you use the graphical framework, you see very clearly. Like you saw that I used pH diagram to explain that thermodynamic heat engine. If you use another kind of diagram, it will not show it to you. So PESTO as a framework, using it as a framework, very important, because we are that T, technological engineering. Like I said, more rains, no problem. If you have more rains, just make your gutters, your channels deeper. Not so, make them deeper. Yes, it costs you money. Yeah, you can get it. And make it wider. Yeah, it costs money. You get it. And so many other things. But while digging, you are digging into other people's, other citizens' environment. That's one. It's costing you money. That's two. It's doing so many things. Yes, go and change siliceous sand, soils in the deserts to zeolite and use them to plant, to grow your plants. You can do it. But there are other problems, other challenges, unexpected results, unintended results will come. So that's why we're saying we should stop using only technological solutions. Rather, we should call in politicians, economists, sociologists, legal people, environmental people, and so on and so forth. It's lack of introduction of these things right from the beginning that's causing all the problems which you have. So PESTO is bring people in political areas, economic areas, social areas, technological areas, legal areas, environmental areas on one single table. So that's what we are saying. We have not been doing it. We should start doing it.
Thank you very much, sir. Quickly go to more comments and questions. Engineer James Namo, thank you so much for your generosity, Prof, sir. Engineer Timothy Sharif, Prof, thanks for the wonderful presentation. Engineer Abdulsalam Mohammed, very concise and educated. Thanks a lot, sir. Engineer Henry Anyebe, thanks, Prof, for this compelling presentation. Engineer Awajogak Ujile, the use of pestle is acceptable, but my worry is the integration of the political class. Are we sure that we can achieve the goal with this class? Prof will make that comment later. We will make comment on that. Then Engineer Solomon Bauer, great presentation, Prof. Any roadmap from Nigerian Society of Chemical Engineers with regards to climate change at the national level? That's another one. Engineer David, we have wonderful presentation, but we need to take another session of this so we can cascade it down to what we all need to do at institutional, organizational and individual levels to help with the commitment to reducing greenhouse gases. That's from Engineer Webb. Then from Engineer Mustafa, say, thank you, Prof, for sharing your wealth of experience in the application of chemical engineering approach to addressing climate change crisis. Engineer Rahim Alabi, thanks to Prof for this insightful presentation. It has exposed us to the thermodynamics of how climate changes, and its attendant consequences. Engineer Usman Garba, all the way from France, Paris. We thank Prof for the presentation. Taking voice and approach, we thank Prof for the presentation. Talking voice and approach took me back to Zaria between 1992 to 1993. Prof, sir, are you considering making a submission to the education group on integrating philosophical approaches to teaching and explaining basic chemical engineering concepts? Wow. And Engineer Amina Madami, wow. I've not seen her for more than 20, 30 years from our undergraduate days. So glad I attended this highly educative and enriching lecture. Professor Adefila retired, but not tired. A true reservoir of knowledge. Been reminiscing my days in chemical engineering at Ahmadu Bello University, Zaria. Yes, we are remembering those days back. Again, Engineer Weird is back. Said, what should be happening in these various sectors, such as oil and gas, etc., towards mitigating and adapting to climate changes challenges, sir? So he's asking, how can other sectoral groups work towards mitigation actions, sir? Then another of your students again, Dr. Olakunle, Engineer Dr. Olakunle, great presentation, sir. It is unfortunate many students and researchers seems not to appreciate this area of thermodynamics. How can the Earth scenario be better analyzed using the heat engine and heat pump approach? Yes, I know you will not differ with Prof that everything can be looked at from heat engine and heat pump. Yes. Then Engineer Amina Damadami, will moving away from fossil fuel solve the problem? How do we balance this with the energy poverty raging Nigeria / Africa? I will again stop again, sir, for Prof to answer the questions that have come up. I think it has been an exciting day today. Sir, you can go ahead and answer the few questions that we raised, sir.
Thank you, everybody. I thank for those complimentary presentations. And thank you all. It seems as if we are bringing Zaria all back. Thank you so much. Commissioner Weep, I know why you are concerned about policies. Your question is, how we can develop policies from all these things that we have said. I think to do that, we need to sit down, just like the Academy of Engineering is looking at reawakening technical and vocational education right now with the cooperation of MBT and co. We have to start thinking of how we can formulate good policies, operate them, and so on and so forth. But coming to this, somebody said, I don't want to mention his name, I know who it is. He said, once we bring politicians. So, Engineer William, but you are here, you're a politician. We have no choice but to work with each other, honestly. That's the reality. Honestly, we all must work with each other. And when you come to look at it, politics has been put above even religion. Our political leaders are superior to our religious leaders. So really you have no choice. And who are these politicians? They're not ghosts. You can also be a politician if you so desire. So we just must work with them. We must work with them. And how do we extend engineering principles to other areas? We have thought about it here. I was discussing with some people yesterday. If you look at your heat engine links the system with the environment. You have your system, then you have your environment, and you have the link between these. And I said in one class that interface, which I talked about in education group, that interface can be looked at as your soul between the spiritual world and your physical world. And all of us know that whether you like it or not, when you see somebody physically, that person has his own mind. That is the soul. He has his own mind. He has something inside his mind. And you have to get what is inside his mind to pull, and others to pull them together and make it a culture and make it a positively oriented culture. So what am I saying? So with what I've said now, it is very easy for us, even as engineers, leaders, to obtain parameters which we are going to be talking about. You could see I brought up parameters of temperature, pressure, enthalpy, and all these kind of things. So you could see that it's very, very easy for us as engineers to start looking into sociology and so on and so forth. And this is an engineering principle. I'm extending this engineering principle, philosophically to other areas of life, to your workplace, to this, to that, to that. Engineering is very, very challenging. Perhaps I talk about it because I had a lot of teaching management for over 30 years in the university. Though I was teaching, but I benefited more than those who I taught. I'm sorry to tell you that. So, engineering, science, and co, they are the basis of most of these things, most of these principles, which you call business and management principles. They are all encapsulated in engineering. And when we have this kind of forum, this kind of platform, I think we can start discussing on this level. If you like, we can come up with a lecture, a philosophical lecture, coming from engineering. For we chemical engineers, our core subjects are thermodynamics and kinetics. Thermodynamics talks about, it happens or it doesn't happen. Kinetics talks about what rate. And every other subject which we talk about are just extensions of this thing happening or not happening, and at what rate. And that's exactly what we have in the world too. So HSE sectoral group, you may want us to look at this and start extending into philosophy from engineering, extending to management from engineering. I'm ready to take part in it. Thank you very much.
Thank you very much, sir. There was a question from engineer Amina Damadami. She said, moving away from fossil fuel, will moving away from fossil fuel solve the problem? How do we balance this with the energy poverty raging Nigeria stroke of Africa? Then one more question from the last question from the chat. The engineer Omodale Eleta said, congratulations, sir. You talked about ozone layer depletion, permitting UV rays to get to Earth and greenhouse gases trapping heat. What is the way forward from the chemical engineering contribution? Then engineer Chuku Nicholas Okagbu, I'm so sorry if I don't pronounce your name properly. Interesting to be part of today's meeting. Prof, thank you so much. Then we have engineer Paul Nwabiekem. Thanks, Prof, for more explanation on pestle. But I believe political will be most compelling as they use politics to control the other parts of pestle. I think that's the last question we have from the chat. Then I'll take two people that will want to talk, sir. I have Professor Elijah Taiwo raising his hand. But before that, I will want Prof to address these two questions raised, sir.
Fossil fuel. My own idea about fossil fuel. We will not go away from fossil fuel. We will continue to use fossil fuel one way or the other. Mind you, we don't want to go into geology and so on and so forth. You know, of all the continents on Earth, Africa is the most stable because it is said that other continents actually moved away from Africa, and Africa is stable. You see that the kind of serious environmental issues which you are having in America and in China and co, we don't have them here. Because of this stability, most of the mineral resources, including fossil fuels, are around us here. And you could see that politically, if we are not being careful, we are going to be moved away from fossil fuel. I'm not saying that we cannot go into renewable energy. No. Fossil fuel will continue to be important. The only thing is that we have to apply better technologies to improve efficiency and effectiveness of using them. We will never go away from using fossil fuel for materials. That is sure. After all, if you come to look at it, what are we? We are hydrocarbons with some nitrogen here and there. So if you are saying we should get rid of all these things, we should get rid of man too. Don't let anybody scare us away from fossil fuels. But we can use less of fossil fuel for energy and use the remainder as material. Because it is the carbon, methane, and so on and so forth that go off from as gases and vapor from this fossil fuel that are troublers of the troposphere. So if we use them in solid form, in material form, and circulate it, that cyclic process within that within that platform we will have less problem. That is my own idea. I'm a thermodynamist. I know that you can get more energy from so many things. You can get energy from just mixing sulfuric acid and water alone. Get energy straight away, just like that, and get it back, and so on and so forth. But we are not going to go away from fossil fuel. We just have to use it more efficiently and more effectively. That's why we are chemical engineers, and we have the ability to do this. But we are being warned, as we are doing this, we should look out to the sociological, economical, legal, environmental aspects. I think we are going to be more conscious of this, going forward.
Thank you very much, sir. Professor Taiwo, please, can you unmute yourself and ask your question?
I wanted to address that ozone.
I'm sorry. I didn't know you've not done that, sir. I'm sorry.
Professor Letter, suggestions have already been raised. So we should stop producing those materials that destroy ozone layer and replace them with something else. The luck we have with all this is that is the digital age that has caused these kind of problems for us. We can use the digital age, also we can use the digital technology also to improve our ability to produce new processes. Okay? So why not? We use what is a problem to solve the problem. And these are the kind of principles that we get from management. You can go ahead.
That's okay. Okay, thank you, sir. Professor Taiwo, can you unmute yourself and ask your question? Professor Taiwo, are you there? Okay, I think he's the only one that wanted to ask question. He's the only one that raised his hand. Okay, and if he's not there, I'll just we'll round up. We'll round up. Thank you very much, sir, for excellent presentation. I think we all enjoyed it. For me, probably this is probably the best I've had from you. This is probably the best I've had from you. Don't be surprised I'm saying so, but I have to tell you, this is probably the best I've had. This is an excellent talk, sir. Thank you very much for your time, for your energy put in making this PowerPoint what it is. For virtually everybody appreciated what you put in. Thank you very much, sir. While Professor Elijah...
Abdulazeez, can I say something?
Okay, go ahead, sir.
Honestly, this lecture was triggered by Mahmoud. Because I had discussed these things with him extensively. All these things which I just was able to put down now, I'm sure you know, there are things which I had in me over 30, 40 years ago, but I didn't put them down completely. I know I used part of it in my inaugural lecture in 1998, but Mahmoud, I must thank you for activating these potentials to what they are today. Thank you very much.
Thank you to one of Prof's senior sons, Mahmoud, for doing excellent. So I will round up the chat section by just one or two. We have your students, Engineer Noel Bali. What an in-depth presentation, Prof. Couldn't expect less. It's a pleasure to be part of this program. Engineer Olalekon Olerewaju, it is interesting looking at other aspects of life from thermodynamics and kinetics. An interesting analogy. Thank you everybody for your time you've had today. I will hand over to the lead HSE, my leader, Engineer Mahmoud Abubakar, to give the vote of thanks. But we already have started giving vote of thanks by thanking him for making Prof to give us this talk that everybody's excited about. So, Engineer Mahmoud, over to you.
Good evening, ladies and gentlemen.
Good evening.
Yeah. Anybody that knows Prof will know that between thermodynamics and his religion, that's what comes first in his mind. There's hardly anything that he cannot use thermodynamics to explain. And for me personally, that has interacted with him right from school and all this while since we left school, my understanding of thermodynamics crystallized after I left school, because when I was school, I almost failed the course. But talking with him every day, trying to explain life situations with thermodynamics and all this, the understanding increased. We've gained knowledge this evening. Definitely, we've gained knowledge. What we do with that knowledge is a different ball altogether. Our earth is, I don't want to use the word sinking, but that's actually the direction it is going. Now, there are three key actions where what we can do to work towards addressing the root causes, which is the reduction in the greenhouse gases, also adaptation strategies, as well as building resilience into our design as chemical engineers or as engineers generally. We can bring this down to individual levels. When we are building our homes, we should build this resilience into it. Let's use materials that will contain heat. Doing that, or cold, doing that will reduce, is likely to reduce your energy consumption. Our drainages, the way we manage waste in our homes, in our community. We should not see that I'm just an individual out of 20 million, 200 million people in Nigeria, or an individual out of 7 billion people in the world. It will not have effect. It will have, because each person clear your own stable, clear your own small area, and you expect that the next person will also do the same, and we have a very good landing. What we are trying to do in solving this, what actually, based on this presentation we've had today, this climate change arises because of we disturb the equilibrium, the thermodynamic equilibrium of the solar system by discharging more than what will be able to maintain that equilibrium. So whatever we do, even if we stop discharging fossil fuel today, we will not be able to return to that equilibrium, but we may return to another equilibrium, which may still not be favorable for us, may not be good for us. So what we need to do individually, the key way, the best way to go is building resilience into our infrastructure, into our design, into the things we do, and also devise adaptation strategy in order to cushion the effects. So with this, in order not to start another lecture, I thank everyone, Prof, for taking time to prepare this. I know 50 slides presented in 20 minutes. I know the amount of work that has gone into this. We thank you very much, sir. Then I heard you say I was the one that encouraged you. I thank God that you are listening to me very well. I also want to encourage you to write a book, sir, to put these ideas that will be able to simplify this thermodynamics for those people that are still remaining in school. Because I remember way back, it was the most difficult thing that we had to grapple with. So, second assignment, sir.
I can't, I've tried. You know, there's something they used to fix it, and I don't want to.
Sorry, I'll take care of that.
Yeah, I also want to thank all the other participants that come today. I think since the beginning of this year, we had our highest participation today. And this initially, Atta was complaining that the participation level is dwindling. Perhaps people have lost interest and all this. But what I learned from this today, if we bring a very interesting topic that capture attention of people, people will come. And that's what we intend to keep doing. So thank you very much, everyone, for coming today. And we hope to see you again next month, last Saturday in October. Thank you very much. Thank you very much, Atta. Well done.
Thank you very much. Thank you very much, my lead, Engineer Abubakar Mahmoud. And thank you, everybody. We've had some other questions from Engineer Mariam Abubakar and Dept. Thank you, everybody, for taking your time. For me, I'm leaving today's talk excited, re-energized that we can continue with this our monthly presentation with the number of people I've seen. Despite the fact that we spent 30 minutes extra, we still have 51 people still online. I mean, what else can encourage one that, yes, we are in the right direction? And thank you, Prof, sir, for making this possible for us. Thank you. We highly appreciate your energy, your time, your mentoring, everything you have given to us. We just simply don't know how to pay you back for what you have done for us. You have taught us not just engineering, you've taught us how to live too. Thank you very much, sir, for the knowledge you have continuously impacted on us. We are grateful. We are very, very grateful, sir. Thank you, sir. On behalf of the Nigerian Society of Chemical Engineers, HAC Sectoral Group, have a wonderful weekend remaining, and we'll see. Let's make it a day and the last Saturday of next month, October. Thank you very much. See you, everybody. Bye-bye.
Bye-bye.
Thank you. Bye-bye.
Bye.
Thank you. Bye.
Thank you. Bye-bye.